Hey, welcome back everybody. We're going to prove a nice little result about the gamma function using mathematical induction. So it turns out for any natural number n, the integral from 0 to infinity of t to the n times e to the minus t dt equals n factorial. And so our proof is going to go a little something like this. So we're going to let p of n be the statement. The integral from 0 to infinity of t to the n times e to the minus t dt is equal to n factorial. And so let's go ahead and establish a base case. And so what we want to do is we want to show that the statement P of 1 is a true statement. And so if I plug 1 in for n, I want to compute this, and we're hoping this equals 1 factorial. So again, we're trying to establish the statement where n equals 1, so that this integral is equal to 1 factorial. So the first thing I want to do is realize that this is an improper integral, so I want to think about it as a limit. So this is a limit as b goes to infinity of the integral from 0 to b of t times e to the minus t dt. This is a classic Calc 2 style integral, so we're going to go ahead and use integration by parts. So u is equal to t, and dv is equal to e to the minus t dt. du is 1 dt, and v is minus e to the minus t. And using integration by parts, we want to work through this. Okay, so let's see what we have here. So here we have the limit as b goes to infinity of, let's see here, so we need u times v, so u times v, so this product, I can think about it like this. That's u times v. And we're evaluating that, remember the bounds, from 0 to b, so that's u times v minus the integral of v du. Well, that has a minus, so v du. So that's not too bad. Okay, I'll worry about that in a moment. Let's go ahead and integrate this. So this will stay the same right here. So this is still minus t over e to the t from 0 to b. And this will be, looks like minus e to the minus t from 0 to b. But I can write these all as one expression evaluated from 0 to b. So I've got minus t over e to the t, and then here I can write this as minus 1 over e to the t, evaluated from 0 to b. All right, let's go ahead and plug in b. So just carrying through with the fundamental theorem of calculus. So this is minus b over e to the b minus 1 over e to the b, minus from the fundamental theorem. Now if I plug in 0 here, that's going to give me 0 over 1, which is 0. And if I plug in 0 here, that's going to give me 1 over 1. So that's 1. So this we can call plus 1, and then we just have to worry about this. So let's think about this for a moment here. Here I have a negative infinity over infinity form. So this term in particular should remind you of a L'Hopital's form. So I'm going to perform L'Hopital's just on this term. I'm going to keep all the rest of this the same. Okay, so let's see what we get when we apply L'Hopital's rule. Okay, so it's going to be minus 1 over e to the b. So if I apply L'Hopital's just on this term here, just going to copy this down. Of course, I'm not applying L'Hopital's here. It's not in the right form. And then this we said was plus 1. And so now we know as b gets very large, this gets closer and closer to 0. As b gets large, this gets closer and closer to 0. And the limit of any constant, no matter where you approach, is that constant. So here I get 0 minus 0 plus 1, which is 1. And that's the same thing as 1 factorial. So this establishes our base case. Okay, our next goal is to move on to the inductive step. So first we want to let n equal some fixed value k. Easy for me to say. So here we go, inductive step. So we want to let n be some fixed k, and we want to assume that that particular statement p of k is true. So what do I mean by this? I mean, I'll say that is, assume that the integral from 0 to infinity of t to the k e to the minus t dt equals k factorial. And again, I'm assuming that for some fixed k, right? Our goal is to show that this implies that p of k plus 1 is true. So let's actually say that. So I'm going to say we want to show that the integral from 0 to infinity of t to the k plus 1 e to the minus t dt equals k plus 1 quantity factorial. And so, i.e., we want to show that if this is true, then this is true. Okay, so let's compute this. And remember, we're assuming that our inductive hypothesis is true. I can use this all I want on my journey of proving that this is true. Okay, so let's observe that the integral from 0 to infinity of t to the k plus 1 times e to the minus t dt is equal to, well, first remember, this is a limit because we have an improper integral. This is the limit as b goes to infinity. The integral from 0 to b, t to the k plus 1 e to the minus t dt. And again, we've got integration by parts on our hands. Okay, so integration by parts. So u is equal to t to the k plus 1, and dv is everything else, so it's e to the minus t dt. And du, I'm going to take the derivative carefully. That's going to give me, it looks like k plus 1 times t to the k, and then dt. And then v, when I take the antiderivative of this, is going to give me minus e to the minus t. Okay, so we want to see what happens now. So just follow this from integration by parts. So I've got u times v, and of course don't forget your limit. So u times v. But I can write that like this. So minus the integral, oh, don't forget to evaluate, minus the integral of v du. So v du, I didn't give myself much space there, did I? You know what? Let's just rewrite that. We gotta give that some breathing room because we've got this k plus 1 here. So let's do this. See, that's real life, folks. That is real life. Okay, so u times v minus the integral with a little breathing room because of this of v du. So v gives me a plus here, double negatives. Du, I've got this factor of k plus 1 in front. And that's t to the k e to the minus t dt. So that was v times du, and that product you're seeing right here. Okay, so after several applications of L'Hopital's rule, I'll leave that as an exercise. So after several applications of L'Hopital's rule, this will go to 0. So that leaves me with the following. So I still have this k plus 1 times the integral from 0 to b of t to the k times e to the minus t dt. And we can actually rewrite that as an improper integral. That's what we want to do. So let's rewrite that as an improper integral, and then keep in mind our inductive hypothesis. Right, so that's going to give me the following. So I've got k plus 1 times the integral from 0 to infinity. So repacking that as an improper integral. And then by our inductive hypothesis, we get the following. So this we said was equal to k factorial, right? That was our assumption. So we've got k plus 1 times k factorial. That seems pretty nice. But that's exactly the definition of k plus 1 factorial. And so we did it. We want to put a nice bow on this with a good conclusion. So we can say, okay, well, was there anything special about my fixed k? No, it's just randomly or arbitrarily chosen. So I'm going to say, well, since k was arbitrarily chosen, it follows by mathematical induction that the integral from 0 to infinity of t to the n e to the minus t dt equals n factorial for all natural numbers n. And that's our proof. It's actually a very, very useful result in mathematics. Very, very nice result.